All right, well, welcome to our webinar titled Elevate Manufacturing with Phillips Additive, Hybrid, and Mastercam's APlus CAD/CAM software. I would like to first introduce our two speakers for today. First is Hamoon Razami, and he is the Training Program Manager and Applications Engineer for CAMufacturing Solutions. Hamoon has more than 5 years of experience in CAD, CAE, additive manufacturing, and the automotive industry. He has a Master's of Science in Mechanical Engineering from the University of Windsor and a bachelor's degree in Industrial Engineering. We also have Brian Christoponis. He is the General Manager of the Hybrid Division for Phillips Corporation. Brian joined the Phillips team in 2016 as an applications engineer for the Federal Division of Phillips, and shortly after became applications manager. Brian now heads up the Phillips Hybrid Division, where he and his team focus on developing customer hybrid applications, building hybrid systems, training new customers, and providing technical support. Before we get started, I just wanted to ask that if you have any questions throughout the webinar, please write it in the Q&A section. You can see on the right-hand side of your screen, not the chat. We will answer your questions either during or at the end of the presentation. And now I'd like to pass the floor off to Hamoon.
Thank you, Sharon. Hello, everyone. I would like to start with an introduction about our company, CAMufacturing Solutions. So our company was established in Windsor, Ontario in 2012, and our main product is the additive manufacturing software APlus. In addition to APlus, we do have different software solutions too, such as an FSW friction stir welding software, which is a joining process, and we do provide consulting services. We are very active in research, and we have different type of video-based and online training available. We are committed to bring additive manufacturing and directed energy deposition to the mainstream. We have a knowledgeable and dedicated team and a collaborative network of partners and resellers. We have users using our software product on 5 continents and over 40 countries as of now. This is pictures of the CAMufacturing team. I am very glad that I work with every individual in these pictures because they are all knowledgeable, reliable, and responsive people. Here, actually, you can see a dome. The reason I have it here is to emphasize that we are very DED serious. That means we don't only work on the software product, but also we try to move DED forward by research. We will talk about this part a little bit more later on. But the main thing I want to say is that we always say that additive manufacturing is not just reverse machining toolpaths. And every single parameter that you see in APlus, we design them and enhance them based on characteristics of DED. And that cannot happen unless we stay ahead by investing in research and forming partners. In the next slide, you can see some of the logos of our partners. Our partners are different software companies, research institutes, universities, colleges, and machine OEMs. Now I would like actually to pass it to Brian in order to give us an introduction about Phillips Corporation and Phillips Additive Hybrid Division.
Thank you, Hamoon. So a brief intro on Phillips Corporation. So for more than 60 years, federal government, private sector, and educational leaders have trusted the experts at Phillips Corporation to solve their greatest manufacturing challenges. Phillips enjoys a 30-year global relationship with Haas Automation, and that has produced over 30,000 installed machines. Our mission is to create legendary value for the manufacturing community by unlocking solutions to propel capabilities, profitability, and productivity. Phillips represents a robust combination of equipment, applications expertise, and services that are well suited to meet the growing range of present and future manufacturing applications requirements. So in this webinar, we'll be talking about our Phillips hybrid solution. And to get started, we really have to start about the technology that we use. This is a directed energy deposition technology from our partner Meltio. So Meltio is who we use for our integration partner inside of Haas machines. So this is a split view of the Meltio deposition head. And a few highlights of this technology. It's a center-fed wire solution. So wire is fed through the very center of the head, and we surround that with 6 independent lasers. So these 6 independent lasers create a hexagonal melt pool with the wire in the center of the melt pool. So this allows us to feed in any XY combination. We can do multi-axis deposition. We're not really hindered because we're center feeding wire. Regardless of which direction we're feeding, the wire is always in the center of the melt pool. We have the ability to maintain wire continuity and check for that during this process. That way, if we ever lose wire continuity with the actual substrate or the part, it will automatically increase our wire feed rate to maintain continuity. So it's a very reliable process that we have inside of these Haas hybrids. It's very easy to service. All the components are modular, where we can swap out laser collimators that actually focus these 6 independent beams, and we can control that where they actually meet the wire very precisely, and we can perform a calibration to make sure that the wire is coaxial to all these 6 independent lasers. And we can also have a programmable hot wire where we can preheat the wire to increase deposition rate, as well as for refractory materials where we can preheat the wire to actually create the melt pool. So this is a short video of Meltio's technology where we're spinning, in this case, a C-axis while depositing material. So the wire will melt just ahead of the actual layer that's being created. And that's where you can see kind of the wire wiggling just a little bit in this video as the wire is going from a solid state to a liquid. And we can precisely deposit material because of this precise laser melt pool. Kind of a quick overview or image of our hybrid integration. So we're mounting this Meltio deposition head on the right-hand side of this, in this case, a Haas UMC 750 spindle. We integrate across the large majority of Haas mills. But regardless of the actual mill being used, we always mount on the right-hand side due to the tool changers being on the left-hand side of the spindle. We focus primarily on wire feedstock for a variety of reasons. One of the biggest is cost. Because we're using commercially available welding wire, it's a very low operating cost. You're talking a factor of 1 to 5 times cheaper. 10 to 5 times cheaper than powder in some cases because of the commodity welding industry. We don't have to have special PPE to handle the wire. It's inert. There's no flammability risk when we talk about these wires that we weld with. At the end of the day, this is still a laser welding process. Really nothing new except we're adding this technology into CNC machines. That way we can deposit and then remachine all in the same system. So conventional, standard operating procedures for welding would be applicable to this technology. Kind of the steps that we take to integrate machines. So we're mounting onto, as I mentioned, the right-hand side of the Haas spindle. Depending on the actual Haas model used, we have specific adapter plates. So we drill and tap into the casting of the Haas mill, and then we indicate our adapter plate square to the machine, which allows us to maintain the machine geometry when we add the deposition head. So that way essentially the W axis or the redundant Z axis is square to the machine tools X, Y, and Z, and then in some cases rotary axis as well. We add laser safe glass to make the enclosure laser safe. That way we don't have to wear additional laser safe glasses. I kind of joke and always say it's like looking through a pair of nice bluely tinted sunglasses. And then we add, additional door interlocks on the side of the Haas enclosure That way, there's no way to open the side doors while we're printing, and that's all interlocked back into the Meltio system. That way, if the door were to ever be forced open, it would automatically break laser security, and you would automatically shut the lasers off if the doors were open. Overall, Meltio's technology, when we talk about, CNC integrations with Haas machines, we're kind of, middle of the pack when it comes to overall part size as well as complexity. When you get into really fine resolution parts, under, 0.5 millimeter track widths, powder bed fusion can certainly make a lot more sense. But we're going after kind of the larger range of applications, parts that would be, casting replacements, or, parts that may be machined from an expensive billet. That's kind of the realm that we're looking for hybrid applications. The fine features, we can get down to about 1.5 millimeters track width and about a 0.5 millimeter high layer height, but we're really focusing more on that 10 to 20 kilogram part range. Overall, because we're integrating into a Haas controller, G-code structure is very straightforward. We have additional M codes to turn on, the actual welding functions, lasers on and off, start wire feed, turn off wire feed, etc. And it's essentially the same G-code you would run on a normal Haas machine. Anyone who is familiar with kind of G-code structure, you can see all the block deletes. We put block deletes on, all of our welding lines of code. That way, if you wanted to turn on block delete, omit those sections of the program, you could, do a dry run on the machine as well. So that's why all the block deletes are on those lines. We use a post processor that we've worked with, post processor developer Postability. So it's one G-code program to, run both the additive and subtractive. We're not merging NC files together. This is all coming from one post processor, one machine simulation. And that's really the point, and why, we've worked so long with Mastercam and APlus and Postability, is to offer this, fully packaged solution where someone's using one software to do, all programming functions of this machine. So, it's very straightforward. We'll get into kind of some of the GUI in Hamoon's portions of the presentation, but it's a very streamlined approach. Mastercam users will see a lot of familiarity when we talk about the additive toolpaths inside of APlus. Now back over to Hamoon.
Thanks, Brian. So before we get to some actual case studies that we are going to talk about them today, I would like to give some introduction about APlus itself too. So APlus is the additive add-on of Mastercam. It supports programming and simulation of additive manufacturing processes in Mastercam, and it's seamlessly integrated into Mastercam with a very familiar interface. That means when user installs APlus on top of Mastercam, they will just get 2 extra ribbon bars on the top ribbon bar. And we try to keep all the toolpath interface very similar to Mastercam. That will make it much easier for the existing Mastercam users to learn APlus too. APlus is optimized for directed energy deposition, but it has a modular software designed to support new and other additive manufacturing processes too. So what is very important here is that APlus is just not like a slicer that you can see. It has a lot of different solutions for different type of geometries and different type of strategies, manufacturing strategies. For example, this part that you can see, it's built with an APlus rotary toolpath on a Phillips hybrid Haas UMC 750 with a 1.2 kilowatts Meltio print engine. So it was built with a rotary toolpath. That means it was built with a continuous deposition without any planar slicing. So if I would like to talk more about different toolpaths, we have 9 different toolpaths and solutions in APlus that you can use them based on the part characteristic and geometry and the strategies that you want to use. If you have a part like this, you can just use one of our planar slices, which is AM slice or AM exact overlap. But if you would like to build something like next picture, it's a rotationally symmetric part. It's a thin wall, so you definitely don't need even to slice it. So you can use a non-planar slicing strategy, which in this case is AM rotary. But if you would like to build on top of cylindrical substrate, for example, the picture you see, or even making a roll die or repairing a roll die, because that's the advantage of hybrid manufacturing, that you can machine, add material, and then machine again. We do have a slicer for that, which is called radial slicing. So it slices your geometry radially, uses a polar system instead of Cartesian, and it's very good for this kind of parts. But if you have a part that you would like to slice it, but not through a normal of a build plane or radially, a part like this, you probably prefer to slice it through the spine, which is swept around it. So that's why we have a spine slice, and it means you definitely have to have a variable layer height, but that is also possible with the software and this Phillips hybrid machine. So on the next slide, we can see more examples of our non-planar builder strategies. For example, the two pictures you are seeing now, they are both spine slice examples. But we do have also another toolpath, which is AM multi-axis surface. So for this toolpath, you just can use any surface in the 3D world. It doesn't have to be planar on any shape, and make a toolpath on it. It's very good to build like turbine blades like this, or even to coat a surface or making repair on an existing mold. Also, on the next pictures, you can see more examples of rotary or radial. These are some of our non-planar toolpaths. So the other thing I would like to emphasize is that when you use hybrid manufacturing and DED, the advantage to other additive manufacturing families are that you can build parts, overhanging geometries, parts with overhang without any support material. It can happen through different type of solutions, but based on what your part is and what your strategy is, we have different solutions. For example, if you want to build the picture on the top left, you would like to use a spinal slice for each pipe, but different toolpaths for each, because they're different shapes. But then you will have to build them one layer at a time, because otherwise you may cause a collision. So we do have merging operations. We have a layer merge, when you can merge based on the number of layers. We have Z layer merge, which Brian will discuss more in one of the case studies. So we have a solution for that. Like if you have the picture on the bottom, again, you can decide if it's a rotational asymmetric part, you can use rotary. If you would like to slice it and just change your tool orientation, you have all those possibilities with the software. Also, your strategy and the way you are building the part, we try to have different solutions for them. For example, if you would like to build a convex dome, it's going to be very easy. You can just use a rotary toolpath and build it on, as shown in this picture. But if you would like to build a concave dome, it's going to get more difficult. So this picture may look familiar from the introduction part. So this is actually one of the parts that our research team worked on it a few years ago, in order to build a concave dome with a 3+2 solution. As you will see in the next picture, our researcher, he divided the part to 45-degree sections and sliced them with those build planes, and tried to keep the nozzle always tangent to the geometry. So build them as with these wedges. So that's the strategy. So we always try to put a lot of effort on the research in order to find new toolpaths or enhance our existing toolpaths. So now I would like to pass it to Brian again in order to get more details on some of the real hybrid case studies.
Thanks, Moon. So the first application that we have is actually the demo that we were running at IMTS back in 2022. And this is a part that we got from one of our Phillips customers on the subtractive side. So Phillips, we sell Haas machines on the East Coast and to the federal government in North America, actually worldwide. But this came through our commercial group for Haas, and they had an application where it's really a casting component, relatively low quantity, and the idea is that we could print this as a casting replacement. We actually printed the entire order of parts for the customer during IMTS and set up. So I think we printed around 13 or 14 of these components at the show, where we use a variety of different toolpaths for additive and subtractive, and built the entire part on this UMC 750 in 2 operations. So the lower section was printed and then machined, and then the spine portion, or the curvature portion, was then printed. That way we could access the lower section with a standard end mill to machine the lower portion, print the spine portion and the top transfer section of the tube, and then do all the final machining and then part it off. So we have a video that'll play in a few minutes or a few seconds, and it'll kind of walk you through the process of how the part was programmed and set up. Overall 3.5 hours, complete both operations. Roughly 3 hours of that was just print time. Rough, ballpark numbers for deposition rate is around about 1 pound an hour, 0.5 kilogram an hour in 316L stainless. So it's a pretty thick wall tube, and we left the inside as printed, as well as the outside of the curved portion of the tube. The inside and outside of both flange sections were final machined on this part. Yeah, so there's a little bit of a delay on the start of the video. So as I mentioned, this is the actual component. It was mounted in a self-centering 5th axis vise to do op 1 on about a 2-inch by 2-inch base, about 6 inch long, that was reusable. So we parted off the part, and it wasn't a consumed build plate. We just simply overprinted on the bottom section. So it prints the bottom section, and then we'll machine the bottom section, print the rest of the part, and then final machine the rest of the part, and then part it off as the last set of toolpaths on the first op of this part. And then it went into another self-centering vise for op 2, which we'll see in the actual real-time video from the show. So we have some simulation and verify of the actual as printed beads, machined, and then back to printing after that series of operations. Final machining of the round portion of the flange. Quick shots of machine sim showing kind of the milling spindle and additive head deposition, or extension of the additive head deposition, and then the actual video. So you can see both setups on the same table. So it's a pretty good application. Really great application for this technology. Especially if you can avoid having a low production run of a custom casting, 316L stainless, and not something that you really could machine easily, if at all, because of that curvature. Avoiding with hybrid, not having to have a drill come in from both sides and try to take a lollipop ball mill to kind of surface machine the inside of that cavity, because the component didn't require it. So much cheaper just to machine just the areas we needed and produce the essentially near net shape via the Meltio deposition process. This is another demo part we ran at a trade show. If anyone had visited us in South Tech in Greenville, South Carolina, we ran this wrench. Obviously, there's much cheaper ways to produce a box wrench or open end wrench. However, this is really a proof of concept showing that we can have dual material components. So the big kind of takeaway behind this is that there is tool steel in the open end portion and the box end portion of this wrench. So it's H13, about 2 beads thick, the entire height of the part. And then the rest is 316L stainless. So if the materials are compatible for welding, we can do functionally, gradient components like this wrench. And we're not limited to kind of like surface cladding or doing an entire layer of a part with a material. We can wire swap really in indefinite amount of times per layer. So you could have just if you wanted to get even more critical with how much material you're using for a higher cost alloy, you could put just the tool steel in the very tip or the radius of the tip of the wrench. You can break the solid model up and create toolpath for that different wire and build this up layer by layer using this Z-layer merge technique to have separate toolpath with different materials. You can also have the same material with different toolpaths and Z-layer merge them as well. But this application was really kind of highlighting the ability to swap wires on the fly and make a dual material component. So this is kind of the operation manager for Mastercam. It's a little hard to see in PowerPoint, but we have additive and subtractive operations all within the same machine group, toolpath group. And we merge those all together. And the next slide will show that. So this is the actual AM merge toolpath, Z-layer merge toolpath, where we can take a bunch of different additive operations and Z-layer merge them up together to avoid, a potential collision. So this is a really great functionality where it's not just limited to working on one part, but you can use this where if you have a build plate and you want to have 10 unique components and have, let's say, one toolpath for each one of those 10, you can then Z-layer merge them all together to have one NC program output all 10 components and build them up layer by layer. You can even do dissimilar layer heights. So maybe you have a component where you want to use a 1 millimeter or a 40 thou layer height. You could have another part using a 0.5 millimeter or 20 thou layer height and still Z-layer merge those together. So super functional tool. I would say almost every single part I program for additive operations, I'm using this Z-layer merge. Sharon, I think you're muted.
Sorry, Sharon, I think you're muted.
Sorry, can you hear me? Thank you, Hamoon and Brian. It was very informative. And now I see some questions coming in through the chat. So let's get started on the questions. The first one says, is there a loss of travel in the X-axis on a typical UMC install?
Yeah, so this question comes up quite a bit. So there is a head shift when it comes to the distance between the milling spindle and the additive head. On a UMC, that's roughly 12 inches, about 300 millimeter. So you don't lose the travel. We don't de-stroke the machine, so we're not changing the limit switch on any of the machines that we've ever done currently. So there's about 35 hybrids that we've built. None of them actually have a physical loss in travel, but when you get into a UMC being a BC configuration, because it is shifted in X, as you rotate that B axis closer to 90 degrees, you're kind of coming into that pinch point. So it's somewhat of a restriction, just like a robot, where you run into kind of a no-go zone where you would have to flip the rotary table the other direction to overcome that kind of area that you don't have when you talk about simultaneous or 3+2 positional deposition work. When you talk about just 3-axis, you can print a cube or a block the same size in XYZ as the Haas machines travel. It's just when you get into tilting that rotary table, when your head is mounted on really a BC configuration. When we do like a VF with an AC configuration, the cubic deposition volume really isn't affected because you're now over top the y-axis versus x-axis.
Thanks, Brian. The next question is, are there any intentions of working towards a more affordable solution for DED additive on the Haas side? And this is someone who is from Ohio and Eastern Kentucky. He says there's a growing interest in our territory, but information is sometimes lacking.
Yeah, so I think one of the things that we really strived for when we came up with this product and working with Meltio for about 3.5 years now is that it's a very low cost directed energy deposition solution, especially for a hybrid machine. We don't admit to being kind of the lowest cost, but we certainly see ourselves as the highest value. And we really think that the Meltio technology in terms of price point pairs very well with Haas.
The next question, is there documentation on how to support these machines and such in our own post-processors? If we encounter a 3 or 4 axis machine, we handle those posts ourselves and like to remain flexible in pricing when possible instead of having to always go to third parties and be subject to their pricing.
So I take that one. Yes, there is an NCI documentation, so you can use that to write your own post if you are interested in doing that.
For 3-axis, I use a modified MP Master for Haas tied into the APlus. Logic works really well.
The next question, is machine simulation working for Additive APlus now?
Sorry, go ahead.
Hamoon, could you answer that?
Of course. So machine simulation for the additive process at the moment, you can simulate the movement, but you cannot simulate the deposition at the machine simulation. However, you can simulate deposition by AM Vision through another function in APlus. So you click on AM Vision and you can see the deposition too, in addition.
Okay, the next question. They say, is that a manual wire swap or do you have dual feed?
So with the Meltio head, there is a parallel wire feed system. So inside the head, you actually have 2 separate head feeders and we have 2 separate external feeders. So we can't do simultaneous 2 wires at the same time, but we can swap automatically. So there's an M code series that we basically retract 1 wire automatically and then advance the other wire into the actual melt pool and then keep maintaining that swap. So it's automatically done from the NC program. You don't have to have kind of the end user operator sit there and hand feed wire to get it into kind of the drive mechanism. It's automatically done. And we've done material builds dual material builds where you might swap 6 or 7 times per layer because of the geometry, trying to weld next to an adjacent deposited area, even though it requires a wire swap. So we can wire swap quite a bit. Happens, hundreds, thousands of times per part, depending on the application.
Thanks, Brian. Next question, is there any form of wipe tower potential cross-contamination or waste from swapping materials multiple times per layer?
So the wire is housed in separate wire liners. So anyone familiar with kind of MIG welding, we're using a very similar wire liner. So they're not the wires are not touching inside of their liners, and the swap only happens in the actual copper nozzle, which is somewhat of a consumable, where you're retracting wire back up inside that copper nozzle and then pushing the new wire in. We haven't seen really any type of cross-contamination because the wire is still in a solid state. It's not like you're dealing with kind of metal powders where you could have kind of cross-contamination of powder being in that same line.
Thanks, Brian. Next question. Let's say that a shop has a Haas machine that they want to add the DED head to. What is the average time to integrate a laser DED system into a machine?
So if it's a machine that we've done before, and I guess getting a little ahead of myself, we do all integrations at a customer site. So originally we had done some integrations at our offices at Phillips, but I would say all but maybe 2 machines we have done all on customer facilities. If it's a machine that we've done before, it takes us about 4 days to go from just standalone Haas machine, fully integrated, test printed, validated. If it's something we've done before. If it's an older machine or a machine that's brand new to us, we'll come on site, take some measurements of the casting. If we don't have CAD models from Haas, some of these older machines can be a little bit difficult to get CAD models for. So we'll come on site, do some measurements, then we'll manufacture the adapter plate, come back on site, and I would say somewhere between a week and 2 weeks, we would have it finished. So these older generations of machines could take us upwards of 2.5 weeks, but average, right around a week for machines that we've done. And we've done UMC 750s, both generations. We've done classic Haas machines, next gen controller Haas machines, VF1s up through VF5s now, and UMC 750s up through UMC 750s up through UMC 1250s.
Thank you, Brian. Have you considered a retractable DED unit to help with the clearance issues you mentioned in the UMC tilt example?
So the head does retract. It retracts up inside the deployment mechanism. When we talk about clearance issues, for machining, there's about a 6.5-inch standoff distance between where the doors close for the deployment mechanism and gauge line 0 on the Haas spindle. So even at B90, there's not really a collision point unless you were working exactly at center line of rotation and using, probably about a 3-inch gauge line holder would allow you to get the tool tip when machining to center line of rotation on a UMC 750. So it's not really any machining hindrance. The whole problem is having a x-axis shift that you kind of run out of x-axis travel. And the big kind of solution to that is rotating the B-axis the opposite direction or having a non-90 degree tilt angle when you're doing deposition.
Is there a rough investment amount for a head in a UMC 750?
So overall, we're about $250,000 to integrate any Haas machine for the Meltio system. That's training, software, the integration, and the hardware.
Is this retrofit just for Haas machines?
So Phillips, we're a very large Haas dealer in the U.S. We cover a large portion of the U.S. on the East Coast. We also have a federal group that covers all U.S. Haas sales for the U.S. federal government worldwide. We have a very large Phillips group in India, also in the Middle East. So we're very, very focused around Haas. We really believe that kind of the price point that we're in with Haas machines and Meltio offer a very high value when we talk about directed energy deposition systems in the market. So we're only focused on Haas right now. I would say if someone's interested in a different integration, we can certainly take a look. Not saying that we could absolutely work with every machine tool partner, but certainly reach out to us and we can see if it's something that we can either introduce you to another Meltio sales partner or work on the project ourselves.
Thanks, Brian. Is the system compatible with all wire materials, or are there specific laser profiles that are ready to go at this time?
Meltio has a standard offering of wire materials. So the general kind of fully supported materials would be, 316L stainless, 17.4 stainless, your mild steel, which is like an ER70 S6 wire, titanium Ti64, Invar just came out, I think, late last year. A variety of nickel alloys like Inconel 718 and 625. So those standard materials that Meltio lists on their website, they have print profiles that have been developed, and they have CT scans as well as mechanical properties for those materials. However, kind of as a general rule, if you can find it in a wire form in a range from 0.35 to 0.45 thousandths of an inch, which is roughly, I think, like 0.75 millimeter to a 1.2 millimeter diameter wire. So if you can find it in a wire form, and it's a material that we can weld, and the large majority of materials, we can process, excluding aluminum alloys and pure copper alloys. Outside of that, we can process it. So Inconel and nickel-based alloys are certainly our sweet spot because of the high cost of the material as well as the difficulty to machining those materials. We print them extremely well. So we focus a lot of time on nickel-based applications and difficult to machine alloys.
Thank you. Looking at the specs of the three Meltio options, the M450 and the robot have hot wire, but the CNC engine says no hot wire. Can the CNC engine use hot wire, or can this option be added to the CNC engine?
We have done hot wire on 3-axis machines. Currently, we have not done any 5-axis Meltio engines with hot wire. It's something that we're looking into for 2024 because what we're doing is introducing a relatively high DC amperage through the actual table. So we have to properly ground the hot wire system. So it's something we're looking at into 24. 3-axis machines, no problem. We've already done these systems, but 5-axis table machines is what we're looking forward to in 2024.
Thank you. Is APlus only compatible with Meltio heads, or will it work with other DED heads?
APlus works with all the DED heads. Either they are laser wire, wire arc, or laser powder, even hot wire. So as long as it's a DED process, APlus works with it. And you can see that it works very great with Meltio heads, as you saw in this webinar.
Thanks, Amun. Is Meltio coming out with a more powerful laser system for faster deposits?
So currently, I really can't speak for Meltio and what their plan is going forward, but they're constantly evolving their technology, and hot wire really is kind of our recommendation for increasing deposition rate.
Based on print parameters, this will differ, but what is the typical part density that can be manufactured?
Your overall density is very close to billet or casting, high quality casting densities. Last night I was looking up specs for a customer on 316L stainless. Density for Meltio was 99.96% in the unheat treated process. We're not hipping. So those familiar with kind of binder jetting metal processes, we don't have to hip. We're getting the density as printed with this laser welding process.
Thank you. Do the different materials handle differently and need adjustments, calibrations as far as deposition rates, height offsets, etc.?
Yeah, this is actually a conversation Hamoon and I were having right before this webinar kicked off. We talk about build parameters, and you can have programmed parameters that are dialed in for a material, but just like machining, your setup is going to dictate what those parameters are for a specific job. For example, if you're printing a part on a 1/4-inch plate versus or 6 millimeter plate or 1/4-inch plate versus a 1-inch or 25 millimeter plate with a pretty big cross-sectional area, that part is going to get a lot hotter. So you're going to get thermal growth. you're going to have to try to compensate for that with layer height, meaning you might print the first layer perfectly at 1 millimeter. So your actual build is, predicted spot on to your programmed 1 millimeter layer height. And I'm just using kind of these numbers as a easy example. And you might print layers 1 through 5 spot on is exactly 5 millimeters. But then as you start printing, let's say layer 5 through layer 6 through layer 10, there's so much heat in that part because you're not allowing it to cool properly because it's a relatively small cross-sectional area. Now that thermal growth is going to throw your layer height off. So you may have to compensate that if you're not doing something to cool. And you could, have an active cooling plate to reduce the heat, reduce that thermal growth effect, or add dwell time per layer. APlus has got some pretty nice features to handle changes in cross-sectional area versus dwell time that can help streamline build parameters across different geometries. But at the end of the day, just like machining, how rigid is your setup? When you talk about that on like the additive front, cross-sectional area comes into play as well as your overall setup.
Is the most common removal from the build plate wire, like powder-based processes, or saw cutoff?
Honestly, we're a little spoiled because we get to work on hybrid machines all day long. So we end up tabbing a lot of jobs off, just like you would with 5-axis conventional machining. So we'll use undercutting slitting saws. We'll use just 1/4 inch high feed mills to overprint, let's say 10 millimeters, and take a 6 millimeter tool to basically tab off the part, finish it in the second op. Or, in some cases, if you're printing a difficult to machine alloy, we're printing Inconel on hot rolled 1/2 inch plates. We'll flip the entire part over and dynamic mill the entire plate off. You're talking about a few dollar build plate that's consumable, and it would be faster to machine and cheaper to machine off completely than it would be to wire EDM. So it really comes down to the application. If we're talking about absolute, speed, or capability of a shop that they have, it really is kind of a mixed group of how our customers cut parts off from plates, as well as what the application dictates.
Could you discuss APlus's thermal simulation abilities?
Sure. So this is actually a very important topic because with the most of the commercial finite element and fluid analysis software, it may take weeks to just simulate one layer of bits. But we have been working on this for a long time. We are working on a heat simulation module for APlus, which will give you a very good idea in a very short time. So that's actually something in development.
Thank you. Can you adjust the layer heights on the fly to compensate for layer height growth?
So from a programming aspect, whatever you post out in terms of G code is going to be ran on the machine. One thing that is nice though, if you're running a program, we can actually manually change the standoff distance of the Meltio head. So it's not something that I really say what is an ideal solution, but if you're running a part for the first time, we can basically adjust up and down, about 3 millimeters of head movement on the Meltio side to offset any error that you may have in your layer height or your layer height prediction that you're using in the APlus toolpaths. Another way around it that, if you're dealing with kind of a difficult to predict layer height, you could machine every, let's say 25 millimeters or every 1 inch to reestablish that printing surface datum. And that would be an extremely reliable process because now your overall error stack up would be reduced to, 1 inch or 25 millimeter of height versus, let's say, 16 inches, of overall build height. But we've been successful in printing very tall parts without having to have any type of machining, but certain applications or materials could require it.
Okay. Well, that is it for today's webinar. Thank you so much for attending. If you need more information, you can get the web addresses off the bottom of the slide, either www.CAMufacturing.com or www.phillipscorp.com/hybrid. Thank you so much, and we'll see you at the next webinar. Take care.